Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Synthesis of Nanomaterials from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, plasma synthesis of nanoparticles is described using various systems. Then, the microwave system is studied and the radiation of energy which is transferred with microwave frequency is discussed in details. The working of AC, DC, and RF plasma systems is studied in this module. Finally, spray pyrolysis technique is discussed and the parameters affecting the film growth are discussed. Let me first introduce you to the plasma synthesis of nanomaterials. Its novel and distinct properties make plasma an important state of matter, which includes positive as well as negative charged particles. For example, electrons, ions, etc., such that the aggregate of all electric charges is zero. The charged species are mixed with neutral gas atoms or molecules, which are also present in plasma. The ionization degree, which is defined by the ratio of charged particles to uncharged particles, may be pretty small. Ionized implies the existence of one or more free electrons which are not associated with any atom or molecule. Plasma is electrically conducting and it strongly responds to electromagnetic fields owing to the presence of free electronic charges. A plasma containing particle is termed as dusty plasma, and dusty plasma is associated with the synthesis. Among the large variety of plasma-based nanoparticle processings, electrical systems have attracted much interest. There are a variety of plasma techniques which can be distinguished on the basis of numerous conditions as follows. Firstly, depending upon the process pressure, plasma can be of two types, namely low pressure and atmospheric pressure plasma. On the basis of thermodynamic equilibrium, plasma are of two types, A. Equilibrium or thermal plasma, where temperature of all species, that is electrons, ions and gas, are equal, and B. Non-equilibrium or non-thermal plasma, wherein the ions and gas are at around same temperatures, but the temperature of electrons is much higher than these two. On the basis of operating temperature, plasma can be divided into two categories. A. Low temperature, which is less than 2000 Kelvin plasma, and B. High temperature, that is more than 2000 Kelvin plasma. Plasma can be divided into several types on the basis of the principle used to generate plasma, such as microwave, radio frequency, AC or DC, electron beam, plasma torch, corona, and electric arc discharge plasma, and so on. On the basis of the type of coupling used, plasma can again be of two types: A. Inductive and B. Capacitive coupling plasma. Depending on the precursors, plasma can be of three types: A. Gaseous, B. Solid, or C. Solution-based plasma. Let us now come on to the microwave systems. In these systems, microwave frequency is used to create the plasma of the material which is required to be deposited. The material needs to be heated by the microwaves in order to create the plasma. Therefore, it is important to consider the energy transferred, that is E, to the charged particle of mass m. Let us suppose that F is the frequency of the oscillating electric field and Q be the charge on the particle. It is well recognized that E scales linearly with Q and it varies inversely with m and the square of frequency f. The magnitude of E decides the temperature of the charged species. Besides possessing ions and free electrons, the microwave plasma also comprises neutral gases, dissociated gas species, along with the precursor molecules to carry out desired chemical reactions. Energy which is transferred to particles is affected by the collisions between charged electrons ions and the uncharged species, that is, molecules, atoms, or particles. Let us assume Z to represent the collision's frequency. The collision frequency scales directly with the gas pressure. Therefore, Z should also be considered in evaluating the energy transferred as follows. E is proportional to Q divided by m into Z divided by F square plus Z square. Since Z increases the gas pressure, E also varies with the gas pressure. Owing to a large difference in temperature of electrons and ions and also between electrons and neutral gas species, the microwave-induced plasma is considered as non-equilibrium or non-thermal plasma. Such plasma is also termed as cold plasma. Because of the overall low temperature in microwave plasma, it reduces the property of particle clustering. It reduces the probability of particle clustering during synthesis process. The schematic representation of calculated relation between Z and E is shown in figure 1 on an elementary species. This is achieved by using two most popular microwave frequencies, that is 0.915 GHz and 2.45 GHz, and also one more frequency which is 5.85 GHz. Figure 1 is a plot of variation of energy transferred with microwave frequency We can also see three different zones for relationship between Z and frequency of the microwave. The following conclusion can be drawn from the figure. First, E decreases with a corresponding increase in the microwave frequency. This is due to the particle formation in the plasma. Secondly, if microwave frequency is decreased, the reaction temperature increases. Third, to decrease the synthesis temperature, microwave frequency should be increased. Fourth, an increase in gas pressure or as Z increases leads to increase in E for Z much less than F. It reaches the maximum value at F is equal to Z and then starts decreasing for Z much greater than F. Since microwave plasma is a gas phase approach, so vaporized precursors are required. The presence of free electrons interferes with the chemical reactions. Thus, microwave plasma offers highly reactive conditions for particle synthesis, high chemical dissociation, as well as ionization of the components taking part in the chemical reactions result in rapid synthesis of the particles. Reactions which are not chemically feasible but thermodynamically feasible can take place at moderate temperatures. The synthesis process involves evaporating a volatile precursor and introducing a suitable reactive gas inside the reaction chamber. The chemical reactions between the compounds are initiated by applying thermal energy. This causes collisions between the molecules, leading to the formation of small crystalline particles by homogeneous nucleation. The size of the particles initially increases due to condensation of molecules on the nucleation site. Further, increase in the particle size is caused by coagulation, followed by coalescence. Eventually, the particles agglomerate, thereby forming big clusters. The agglomeration can be prevented by rapid quenching. In microwave plasma, particle formation is enhanced by ionization, particle charging, and dissociation of the compounds. Nucleation is critical towards particle synthesis as the particle size variation is influenced by the number of nucleation sites which are present in plasma. The nucleation process differs from the classical homogeneous nucleation from supersaturated vapors. Rather, it is described as a chemical clustering mechanism which is determined by the chemistries of the reacting species. These species are different for different material systems. Thus, a general nucleation mechanism is difficult to predict. Synthesis conditions can be selected so as to produce particles carrying like charges, that is, all particles carrying either positive or negative charge. This prevents particle growth via coagulation, coalescence, agglomeration due to Coulombic repulsions among likely charged particles. Microwave plasma may produce highly uniform sized particles in comparison to the conventional gas phase techniques if all particles are made to be evenly charged. Thus, non-thermal microwave plasma can be expected to produce nanoparticles with narrow size distributions. Let us now discuss the various parameters which are influencing the growth of particles. Parameters which are influences the growth of particles include microwave frequency, cavity design, system temperature and pressure, microwave power, residence time, type of precursors and their concentrations. Some of these parameters are interdependent. For example, any increase in the flow of gas does not only increase the pressure of gas, but it also causes an increase in the temperature. Temperature affects the collision and the residence time as well. Additionally, microwave power can directly influence the system temperature. These interdependencies are further complicated by the effect of pressure or particle charging and selective particle heating. Therefore, any discussion of influencing parameters is highly complex. We next discuss about AC and DC plasma systems. Elevated temperature plasma techniques are the most popular and were the earliest to be used. They operate at ambient pressures and they work on electrical power which is produced by DC, AC or RF sources. Energy distribution in these plasma systems is typically close to thermal equilibrium. Figure displays two types of assemblies which are used for powder synthesis. They can operate both on AC and DC power. The plasma is created between two coaxial electrodes and a powerful gas stream blows it out of the system. The gas stream is used for two purposes. A. It works as the reactive gas for the plasma. And B. It avoids overheating of electrodes. Higher power systems may have an integrated water cooling system. Suitable reactive gases which are required to produce the desired particles may be added. These arrangements differ in the manner precursor is supplied. The precursors used may be a solid powder or liquid precursor in a solution. The solution-based precursors strongly affect the energy of the plasma flame. The axially fed precursor is injected in the chamber by the coaxially introduced gas stream, thereby avoiding the need for any pump for the precursor. Any unplanned deposition of product in the system is prevented by a circumferential sheath gas which is introduced in the nozzle system. Powder precursors are generally fed directly into the plasma flame from sides. The temperature in the plasma is extremely high, of the order of 4000 Kelvin, such that the metals and the majority of oxides are already melted or evaporated. Thus, as the precursor evaporates, there is no problem of particle or droplet size. Nozzle design is the crucial parameter which influences the synthesis. Nozzle designs vary depending upon the gas velocity which is required for the particular process, from simple to highly sophisticated, having hypersonic gas velocities. The particles in plasma move randomly in the direction of the gas stream. Therefore, there is high probability of particle collisions, which may result in clustering or agglomeration. To avoid particle clustering, rapid quenching is often used. The quenching zone should be properly designed for ensuring high quality product information. The quenching gas can be introduced into the system either radially or axially against the flow direction. Nonetheless, AC and DC plasma systems suffer from producing highly clustered forms of powders. Let us discuss next about the RF systems. In synthesizing nanoparticles via RF plasma method, the plasma is produced by RF coils. The precursor is kept in a vessel and the vessel is placed inside the evacuated chamber. The high frequency RF coils heat the precursor above its evaporation temperature. Helium gas is introduced inside the chamber to form a high temperature plasma around the coils. Helium gas atoms act as nucleation sites for the precursor vapors. These vapors then diffuse up to a cold collector rod to be collected as nanoparticles. And lastly, the produced particles are passivated by introducing suitable gas such as oxygen. A schematic of the RF plasma system is shown in the figure 3. We can see the setup of inductively coupled plasma device for nanoparticle synthesis. The precursor may be supplied either axially or radially. The process gas and precursors are introduced into the system analogous to the AC and DC systems. The frequencies applied in this case vary between 50 kHz and 10 MHz. The difference between AC or DC and RF systems is that the latter works without electrodes. Thus, contamination from electrodes is not an issue. Additionally, RF systems do not have wearable parts with limited service life. Further, consumable electrodes cannot be employed as precursors. The quality of the product can be improved by quenching in inductively coupled RF systems. We will next discuss the spray pyrolysis technique. It is a simple and economic procedure to deposit a wide range of thin films suitable for use in different devices, including sensors, solar cells, etc. It can be employed to produce thin as well as thick films. Also, ceramic coatings or powders can be produced using this. Films of almost any composition can be produced via this method. A standard spray pyrolysis instrument includes an atomizer, the precursor solution, a substrate heater, and a temperature controller. Atomizer use can be of any of the following types: A. Air blast, that is exposing liquid to an air stream. B. Ultrasonic, that is using ultrasonic frequencies to produce short wavelengths which are required for sufficient atomization. Or C. Electrostatic, that is exposing the liquid by high electric field. Figure 4 shows the schematics of the equipment which is used in spray pyrolysis technique. Typically, spray pyrolysis includes spraying of the metal salt solution on a preheated substrate. The drops sprayed onto the substrate stretch as discs and are thermally decomposed. The size as well as structure of these discs depends on momentum and size of the droplet along with the substrate temperature. Accordingly, the film is mostly formed of the overlapping metal salt disc being transformed to metal oxides on heated surfaces. We will next discuss about the useful parameters in spray pyrolysis. The following parameters affect the structure and properties of films which are deposited via spray pyrolysis. First one is the temperature. This technique includes several processes which are taking place either at once or in succession. Secondly, these include aerosol formation and transportation, solvent vaporization, droplet impact, together with successive spreading and decomposition of precursor. Deposition temperature influences all these processes barring the aerosol formation and transportation. Therefore, temperature of substrate is the most important parameter which determines the structure and properties of deposited films. With rising temperature, film morphology transforms from cracked into porous. Second parameter is the precursor solution. Precursor is the next most critical process variable. The solvent, concentration, and type of salt and additional additives affect the chemical and physical properties of precursor. Consequently, The properties and structure of the deposited films may be controlled by altering the composition of precursor solution. So students, let us now summarize what we have learned in this module. In this module, plasma synthesis of nanoparticles was described using various systems. Then, the microwave system was studied and the variation of energy which is transferred with microwave frequency was discussed. The working of AC, DC and RF plasma systems was studied. Finally, spray pyrolysis technique was studied and the parameters affecting the film growth were discussed. Thank you students for your attention.